Yeah, hi everyone. So welcome to this lecture number 6 of week 7 on the course on linear systems. In the previous lecture, we saw about some details about what if the system is not completely controllable, and we had devised methods in a way where we could actually split up the controllable part and the uncontrollable part. And what we also saw how this changes the transfer function, in that the transfer function is actually the transfer function of only the controllable part, and things related to the uncontrollable part do not actually show up in the transfer function. And this actually shows up as some kind of a pole zero cancellation, which some of your undergrad control courses would have already taught you. Okay, so today we will look more of what we can do with this uncontrollable systems. Is there some hope in with those systems, or can I at least do some partial design and things like that. So before that, before we define the general notion of stabilizability, we will start in general of what is a feedback stabilization for a general controllable system. So we start with maybe asking some questions, right. So say I have the pair A comma B, which is completely controllable, and just recollect that. So whenever we do talk about pair A and B being controllable, we don't necessarily talk about the stability of the A matrix or not. So those conditions were not necessary in deriving controllability properties. So the controllability properties is independent of whether or not the A matrix is a stability matrix or not. Okay, so the question that we can ask is the following. So if A is unstable, right. So unstable essentially means there is at least one eigenvector on the right half plane, or at least there is one unstable pole, or one unstable eigenvalue. So is it possible that this system can be made stable via some control law? Okay. Now where does the control appear? The control appears here. So assume my control is of the form u equal to minus kx, which is also called a standard state feedback controller. Okay. So can this system be made stable via some control law? So A is unstable. So what happens when I use this control law? The system dynamics becomes Ax plus B minus Kx. So this is A minus B times Kx. Now I look at this matrix and ask myself a question: is this stable, right? So this matrix, which is the closed loop A matrix or the system matrix, is this stable? So can I do a control K in such a way that the closed loop A matrix, let me call this A tilde, is a stability matrix? Okay. So this is the question we will ask about for ourselves, about can we stabilize a system via feedback, or also called as feedback stabilization. Sorry. Right. And then how do we check for these conditions based on the techniques that we learned so far? So some questions that we will ask ourselves. So if the pair A comma B is controllable, what can I say about the pair minus mu I minus A times B? You can check that whenever A comma B is controllable, this pair is also controllable. You can use any one of those tests, starting from the rank condition to the eigenvector test and so on. Okay, a little exercise you can do, which I possibly the answer will be obvious later in the lecture. So, if I have some eigenvalues of A, how are these eigenvalues related to the eigenvalues of minus mu I minus A? So, this essentially is the identity matrix of appropriate dimension. Okay, so what does this mean, right? So, if A is not a stability matrix, that A is unstable, can we choose a mu sufficiently large that makes this a stability matrix? Okay. Now, the next question is or the final question that we will ask, or which we even motivated ourselves in this lecture, is if A is not a stability matrix, can we find a control law that stabilizes the system, and under what conditions can I actually find a control law that stabilizes the system? Okay, so let's come back here. So, AB being controllable also means minus mu I minus A comma B is also controllable. Okay. Now, mu can be just any number, nothing that it must be positive or negative, it could be whatever in R. Okay. So, let us actually verify this. So, what we know about the eigenvectors, right. So, what is the relation between the eigenvector of A transpose and the eigenvector of mu I minus A transpose, which is, okay, I am just taking the transpose of this entire thing, minus mu I minus A transpose. Okay. So, when x is an eigenvector of A transpose associated to this eigenvector lambda, this is also same, minus mu I minus A transpose x is minus mu minus lambda x, okay, which means this A and this mu I minus A transpose have the same eigenvector x. Sorry. And therefore, a certain pair lambda minus x is an eigen value and eigenvector pair for A transpose if and only if minus mu minus lambda comma x is an eigenvalue eigenvector pair for minus mu with the identity minus A transpose. Okay. So, this kind of answers this first question, right. If the pair AB is controllable, what can we say about the pair minus mu I minus A comma B, and then okay. So, once they have the same eigenvectors, then the result follows from the eigenvector test for controllability. Therefore, by choosing mu sufficiently large, I can make this matrix minus mu I minus A transpose to be stable, or the transpose of this is also stable because A and A transpose necessarily have the same eigenvalues. I think this was said earlier, and you can also verify it for yourself. Okay. Now, suppose that I choose a mu large enough such that mu I minus A transpose is stable, or this also means that minus mu I minus A is also stable. Okay. And then from the Lyapunov test, what should happen? Well, minus mu I okay, or equivalently I can say that A W plus W A transpose minus B B transpose is minus 2 mu W. Okay, where do I get this from? I get this from this theorem which we had earlier, right. So, if A is a stability matrix, so in this case this A turns out to be this mu I minus A. So, whenever this is a stability matrix, the LTI system is controllable if and only if some relation like this holds. Okay. So, I am just writing that exactly the same relation, sorry I missed a minus here, exactly the same relation with A replaced by this matrix, and therefore, equivalent condition now I have for mu to be sufficiently large such that minus mu I minus A transpose is stable looks something like this. Okay. Now, what I can do is multiply on the right hand side of the equation by some P inverse. Okay. So, what will I have now, let us say P equal to W inverse, and I multiply both equations from the right hand side with this. So, what I have is A W P plus W A transpose P minus B B transpose P is, okay, I will do this on both sides, P here, P, and this is equal to minus twice mu a P here, W and a P. So, this will result in an equation which looks like this, P A plus A transpose P minus P B B transpose P is minus twice mu of P. Okay. This can be further written as P A minus B K plus A minus B K transpose P is minus twice mu P. Okay. This is when K is chosen as half B transpose P. Okay. Now, what do we know, that P is greater than 0, right. So, this matrix which I multiply on both sides with a P, because W is greater than 0. So, this P will also be greater than 0. Okay. Okay. So, this kind of resembles a Lyapunov equation, right. A transpose P plus P A is minus Q. Okay. So, what do we conclude from all this, right. So, this P A tilde plus A tilde transpose P is say I just call this as minus Q, right. So, where does this A tilde come from? This is the A matrix of the closed loop system. So, okay, let's run through these steps again. So, I want to find out. So, the question I asked to begin with was, let us have a system A x plus B u. A may not be necessarily stable. Can I make this system stable via some feedback control law of the form u equal to minus k x, and if such a k exists, how should that k look like? Okay. So, I follow these steps all the way, and what I get is this. Okay. Now, this means that the closed loop system is stable. Okay. So, I can sum up all this into the following, that when this system is controllable, that in that case for every mu it is possible to find a state feedback controller of the form u equal to minus k x that places all the eigenvalues of the closed loop system to the left of minus mu. Okay. So, that you can easily verify from here. So, not only that this system stabilizes this input law, not only does it stabilize the closed loop system, but it also places all the eigenvalues to the left of minus mu. Okay. So, this is a good indication of why if the system is completely controllable, I can place all the eigenvalues of the closed loop system in such a way that they are stable, and not only stable, they are also relatively stable in a way that all the eigenvalues are placed to the left of minus mu. Okay, this also similarly we did while we were doing the Routh-Hurwitz criterion, which not only gave us information of stability, but it also gave us information on the relative stability. Right, but by a little change of variable, I could find out if all the poles of the closed loop system were, say, for example, to the left of minus 1 and so on. Right. So, this is a similar test, right. So, and this you can easily verify by the properties of the A matrix here, right, starting from here. Okay. Now, let us get back to where we began with, right. So, we began with the controllable decomposition. Okay, before that a similar result also holds for the discrete time system, where I can, with the help of some feedback control law, restrict all the system, all the complex all the poles in the complex plane to be within a disk of size less than or equal to mu. So, since for example, maybe this is my stability region, this is my unit circle, I can also place all the poles in such a way that they are less than some disk of radius mu. And so, this is essentially what it means in the complex plane, which is in necessarily the z plane in the case of discrete time systems. Okay. Now, let us get back to stability tests when I do the controllable decomposition for cases where rank of C is q, which is less than n, which means the system is not completely controllable. Okay. What is the notion of stabilizability in this case? Right, when the system is not completely controllable. When the system is completely controllable, I know that any control law of the form u equal to minus k x just derived will place all the closed loop eigenvalues to wherever I want. We will learn these methods of how to appropriately place them in the coming lectures. So, that is not the objective of what is the appropriate design, but at least now I know that if the system is completely controllable, I can place the poles accordingly. I can at least go from an open loop unstable system to a closed loop stable system. Okay. What happens when the system is not completely controllable? Well, in this case we say that the pair A comma B is stabilizable. Earlier we had talked about the pair being controllable, but now we talk of a little weaker version, that the pair A B is stabilizable if it is algebraically equivalent to a system in the standard form with n being equal to q, which means the system is completely controllable. Right. And if it is not completely controllable, then what do I do? Well, then at least okay, should be a u here. Then at least I must ensure that A u is a stability matrix, because the dynamics of x u evolve according to A u x u. And there is no influence of control input, right. So, there is no u here. Okay. So, and this evolve autonomously by themselves, and if x u is if A u is unstable, then x u will go unbounded as time goes to infinity, and therefore, even if I can control the remaining parts, the system by itself is inherently unstable, and therefore, for me to do anything with the system, I must ensure, or what is the necessary condition is that this A u must be a stability matrix, right. So, only then I can say that the system is stabilizable, that if the uncontrollable part of the system should is stable, right. So, this is what it means, right. A u being a stability matrix means the uncontrollable part of the system is stable. Okay. So, yeah, so how do we test this? In continuous time, the continuous time LTI system is stabilizable if and only if every eigenvector of A transpose corresponding to an eigenvalue with a positive or 0 real part is not in the kernel of B transpose. We will slowly do this proof. The proof will largely be based on the eigenvector test that we had for controllability. Okay, so let's begin by doing this proof. Right. So, what do I need to show? That stabilizability is equivalent to saying that every eigenvector of A transpose corresponding to an eigenvalue with positive or 0 real part is not in the kernel of B transpose. Okay, so again we will assume one and then prove the other, and then second we will assume this and then prove this one. Okay, so let us assume stabilizability, right? The first part will okay. Assume stabilizability, and also that there is a similarity transform T which will take my system from A to this controllable decomposition form AC, so 0 AU via T inverse AT. Similarly, B will be PC 0 T inverse B. Okay, now assume stabilizability and check what happens with every unstable eigenvector of A transpose and check if it is in the kernel of B transpose or not. Okay, we as usual prove by contradiction. Okay, which means assume that there is an unstable eigenvalue vector pair lambda comma, let me call this E just to avoid confusion in notation, for which A transpose E is lambda E and B transpose of E equal to 0. Okay, the E is an eigenvector corresponding to the eigenvalue lambda. So, what does this mean? So, this A I can write in terms of A bar. Right. So, from here A bar, this A would be T A bar T inverse transpose E is lambda E. Similarly, T B bar with the transpose times E equal to 0. So, this is just a little modification of this here, just plug. So, here I am writing A transpose, or sorry, A bar in terms of A, and here I write A in terms of A bar. Okay. Now, this can also be written in the following way. So, I have T, the inverse and transpose, let me call it minus T, A bar transpose, T transpose, E is lambda E. And also here I can write this alternatively as B C transpose 0, T transpose E equal to 0. This I can okay. So, what does this simplify to? This simplifies to, how does A transpose look like? A bar transpose. A bar is something like this. So, I will have A C transpose, A 1 2 transpose 0 here, A U transpose. Okay, this will just be a T transpose here. Okay. T transpose, I just take this T to the other side, and what I will have is lambda T transpose of E. Okay. So, there is a E here. Okay. So, let me write this in the following way: A C transpose 0, A 1 2 transpose, A U transpose. Now, this T, let me write this a little properly, T transpose E is an eigenvector of A bar transpose corresponding to the eigenvalue of lambda. So, this is the eigenvector, and let me call this eigenvector E C and E U, right, where E C transpose E U transpose is T transpose of E, and this is not equal to 0. I am just splitting this eigenvector into say some controllable and the uncontrollable part. Okay. So, this will be equal to, on the right hand side, lambda times E C E U, and similarly B C transpose 0 E C and E U is 0. Okay. Now, what do we know? We know that, one, that the pair AC BC is controllable. Okay. And then if I just write this down, I have AC transpose EC is lambda times EC, and further from the second thing I will have BC transpose EC equal to 0. Okay. And what is also the assumption that EC is not equal to 0, and therefore, so I have found a eigenvector lambda of AC transpose, which is the controllable part of the system, in the kernel of BC transpose. So, this violates the eigenvector test. So, this means that if there is an unstable eigenvalue eigenvector pair, then this lambda, which is unstable, must be in or must be an eigenvalue of AC, sorry, AU, the uncontrollable part, because again AU transpose EU is lambda EU. Again, now this again contradicts because my system is stabilizable. which means A2 must be a stability matrix, and this lambda which got kicked out of here is finding a place in AU. Well, it cannot be in AU, this unstable lambda cannot be in AU necessarily because of the assumption of stabilizability. Stabilizability always meant that the uncontrollable part is stable. Therefore, every eigenvector of A transpose corresponding to an eigenvalue with positive or 0 real part is not in the kernel of B transpose, right. That is what we proved in this case. Okay. Now, conversely, suppose the system is not stabilizable. Okay. If the system is not stabilizable, then AU or AU transpose, both of them has at least one unstable eigenvector or eigenvalue. So, which means AU transpose EU is lambda EU, where EU is not equal to 0. Then the A bar transpose of this EU, which reads like this. So, I have AC transpose 0 here, A12 transpose, AU transpose 0, EU is lambda 0 and EU. Okay. And B bar transpose 0 of EU is B C transpose 0 0 EU is 0. Again, this eigenvector is not allowed to be 0. Okay. So, what does this mean? That we have found an unstable eigenvector of A bar transpose in the kernel of B bar transpose, and therefore, this pair A bar B bar cannot be stabilizable. Okay. And so, if this A bar B bar is not stabilizable, then it is easy to conclude that the original pair A B is also is also such that this eigenvector x is let me call this E, an eigenvector E which is T transpose inverse 0 times EU comes from 0 EU is T transpose E. This eigenvector is an unstable eigenvector of A transpose in the kernel of B transpose. Okay. Therefore, well, this concludes the proof. Okay. So, we started with the assumption of system not being stabilizable and found an eigenvector of A transpose, an unstable eigenvector of A transpose, which is in the kernel of B transpose. Okay. Similarly, I can write down a result for the discrete time, where we are looking at eigenvalues with magnitude larger or equal to 1. Okay. I will just read out the PBH test. We will not go into the details of that. So, the continuous time LTI system is stabilizable if and only if the rank of this matrix is n. Similarly, for the discrete time systems for eigenvalues which satisfy this relation. I will not really go into the details of this. It is a straightforward proof coming from the controllable case. Okay. So, now coming back to the stabilizability of systems which are possibly not completely controllable, right. So, we say that the LTI system is stabilizable if and only if there is a positive definite solution P to the following Lyapunov matrix inequality. Okay. A slight contrast to what we had over here, right. So, we assumed that A was a stability matrix, then the LTI system was controllable if and only if there existed a unique positive definite solution W to this Lyapunov equation, right, and where W was given by this little expression here. Okay. So, here there is a nice equality, whereas here we also see that the sign of the B transpose is reversed and there is a strict less than strict inequality. Okay. We will slowly try to prove this and see also on the way why these conditions are look a lot different to the conditions over here. Okay. So, let us try doing a proof for this. So, stabilizability okay. So, I am just doing the Lyapunov test for stabilizability is equivalent to solving A B plus P A transpose minus B transpose less than 0. Okay. So, as usual I will just do for the continuous time, and the discrete time version will be a direct consequence of this. Okay. So, we start by showing that if this equation, let me call this star, has a positive definite solution P, then the LTI system is stabilizable. I show this way first. Okay. So, I just again invoke the eigenvector test. Right. So, what was the eigenvector test? Just let's recall again that the continuous time system is stable if and only if every eigenvector of A transpose corresponding to an unstable eigenvalue is not in the kernel of B transpose. Right. Okay. So, assume that this is true, that is what we will show, that we will assume this to be true and show that the system is stabilizable. So, let x not equal to 0 be an eigenvector of A transpose with unstable eigenvalue, right, that is A transpose x is lambda of x. Okay, then what we must show? We must check if this x is in the kernel of B or not. Okay, so let us check with the help of this inequality. So, this will be less than or equal to x transpose B transpose x. and this also I can write as the norm of B transpose X the whole square. Okay, this is again the complex conjugate and so on. So, I do all the steps as I do for in the earlier versions of the proof. So, I get twice the real part of lambda x star p x on the left hand side, and then of course, I have a B transpose here. What do I know is that this eigenvalue is either positive or 0. Therefore, this will be something like this, twice real part of lambda x star p x, and now this is strictly less than B transpose x square, okay, which means that if lambda is an unstable eigenvalue, or because or we start with the assumption that lambda is an unstable eigenvalue, this B transpose x is always greater than 0, and therefore, this eigenvector x must not belong to kernel of B transpose. That was what the statement was, that if and only if every eigenvector of A transpose corresponding to an unstable eigenvalue or eigenvalue with a 0 real part, that is this guy, this is should not be in the kernel of B transpose. So, this unstable eigen value is not in the kernel of B transpose. Okay. Therefore, I can conclude stabilizability. And the strict less than here is because I also allow for 0 eigenvalues, right. If there is, instead of strict equality, say I have an inequality like this, then there is a chance that okay, B transpose x can also be equal to 0, right. So, that is just to eliminate that condition. Okay. Right. Now, we do the converse proof. Converse proof would be that we assume stabilizability. Okay. Now, assuming stabilizability, I can do this. A bar is A C A 1 to 0 A u, which again comes as T inverse A of t. B bar is B C 0 T inverse B. Okay. Now, if the pair AC BC is controllable, if the pair AC BC is controllable, so the first result of today showed us something like this, right. If the pair AC BC was controllable, I could write it something like this, right. So, we make use of this result here, and okay, call this my Q matrix to equivalently write a condition here, that okay, I just take the controllable part PC plus PC AC transpose is minus QC, and this is always less than 0, and because of the controllability, and then PC is greater than 0, it is symmetric and so on. Okay. Now, second is if I assume that the system is stabilizable, which means AU is a stability matrix. Right, and whenever U is a stability matrix, I can invoke the Lyapunov theorem, which says that there always exists a PU which is symmetric and positive definite such that this holds is minus QU, which is less than 0. Okay. Now, what I have to show is that if this and this are satisfied, which means where do these come from? This come from the assumption of stability. Whenever these two are satisfied, can I show a condition like this? Okay, which means can I construct a new P based on this P here and this P here, PC and PU. So, let me just define P bar as the new P, which is PC 0 0 rho of PU. Okay. Now, for some scalar rho greater than 0, let me just check what happens with this inequality. A bar P bar plus P bar A bar transpose minus B bar transpose. Right, that is what the thing which I wanted to verify. Okay. So, let us see what happens with this. So, A bar is AC A12 0 AU. How does my P bar look like? P bar is PC 0 0 rho of PU plus the second term I again have a P, which is PC 0 0 rho times P of U. Okay. And then A bar transpose, this is AC transpose 0 A12 transpose and AU, okay, minus BB transpose. How does the B bar or B bar transpose? That looks like BC 0, BC transpose and 0. Okay. Now, I make use of this condition and I make use of this condition. Okay. So, this will just simplify to QC minus rho A12 PU minus rho PU A12 transpose and rho of QU. Okay. So, whenever rho is greater than 0, this is always less than 0. Okay. That is what we wanted to show, that whenever system is stabilizable, then I can solve for a matrix inequality which looks like this, right, this condition. Now, we showed this for the transform system A bar B bar. Now, this can be easily translated to A, the pair AB, just by choosing the P matrix to be something like this: T PC 0 0 rho PU T transpose. Okay. So, I will leave this proof for you. So, it means to say that whatever property is holding for A bar B bar, it also holds for this pair A comma B. Okay. So, that kind of concludes the proof, which is essentially the Lyapunov test for stabilizability. Okay. So, the last result that we will do today is about feedback stabilization, right, feedback stabilization in the sense of what if the system is not completely controllable. Okay. So, the result looks something like this. So, when the LTI system is stabilizable, it is always possible to find a state feedback controller that makes the closed loop system asymptotically stable. Okay. So, this AC can be unstable to begin with. AU is a stability matrix because I assume that that this is stabilizable means the uncontrollable part is stable, plus BC 0 here and a U. Okay. So, when this system is stabilizable, which means AU is a stability matrix, then with some control law of the form U equal to minus Kx, I can make the system to be asymptotically stable, which means I can place all the poles of AC or I can assign whatever values I want to this matrix AC to the left of minus mu or whatever we did in the previous case. Okay. So, the proof is very similar. So, we begin with so we do a little reverse, right. So, let us say I have a system x dot is Ax plus Bu with a controller of the form U equal to minus Kx with K being this one, and then I just invoke the Lyapunov test for stabilizability. and the Lyapunov condition for this stability. Okay, let's actually do this and check what it means. Right. Okay. So what do I know is x transpose, sorry, x dot is A x plus bu is stabilizable. Okay, which means that AP plus P A transpose minus B transpose is less than 0. Okay. Now define. So again this P is greater than 0, symmetric, and so on. Okay. So where does this come from? This stabilizability test comes from just the previous theorem that we had here. Okay. Now if it is stabilizable, this condition holds, and define K to be half B transpose P inverse. Okay. And I can write this inequality in the following form: A minus half B transpose P inverse P plus P A minus half B transpose P inverse is again very similar to what we had before, right? A minus B K P plus P A minus B K less than 0. So again multiplying this equality both from the left and right by Q is P inverse, sorry, Q is as P inverse, I get Q A tilde, if I call this A tilde, plus A, sorry, A tilde transpose times Q is less than 0, right. Now this is the Lyapunov condition for stability. Okay, which means that this A tilde is now a stability matrix. Okay, which essentially means that with the application of this control law u equal to minus kx, I can get this A minus pk to be a stability matrix. Okay, and this will it will eventually turn out, and we will do a little proof of this while we do the control design, that these are both necessary and sufficient conditions for stabilizability, or even in the earlier case, right, when we had a completely controllable system, those conditions were both necessary and sufficient. Okay, so so we talked today about stabilizability, and then how can I stabilize, or is there a possibility to stabilize a system via feedback. Okay, so so the next lecture we will start with covering the basics of observability, constructability, and its weaker form called detectability. Okay, so that's coming up next week. Thanks for listening.